All right, let's talk about the chain rule here. Chain rule. Now, the chain rule is really helpful because it allows us to take the derivative of composite functions, which are, you see composite functions all over the place. So being able to take the derivative of them is something that's really, really helpful. All right, so let's take a look first off at kind of the math equations and how you'll see it in the textbook, and then we'll kind of go over it a little bit more practically through a few examples. So first off, we have the change in y with respect to x equals the change in y with respect to u, and the change multiplied by the change in u with respect to x. And if you look at this, this sort of makes sense if you think about it. We're looking ultimately at how y is changing with respect to x. So we're really taking y with respect to u, so how y is changing with u, and then how u is changing with x. So at the end of the day, we're going to have how y is changing with x. We just go about it because we're looking at composite functions in this almost two-step process. So let's look at it in terms of kind of how another way that you'll see it. So if we're taking the derivative of f of g of x, a lot of parentheses there, you're just going to take the derivative of f and leave g of x by itself. We're not going to leave that untouched. So just the derivative of the f, the outside function. Then we're going to multiply it by the derivative of this inside function. So we have f prime of g of x times g prime of x. So looking at this maybe in a two-step process here, the first thing that we're going to do, going to take the derivative of the outside function when you look at a composite function. And then the second thing you're going to do, you're going to multiply it by the derivative of the inside function. And that's really what it is. You take two derivatives, and then you're going to multiply them together. So let's take a look at this with a few different examples. All right, so let's say you're going to take the derivative of 3x plus 1 cubed. Okay, now, so to make this a little bit easier to see, let's go ahead and rename this 3x plus 1, right? Let's say that u is going to equal 3x plus 1, because that's just my inside function. Well, if u equals 3x plus 1, then what I'm doing here is I'm just taking the derivative of u cubed. Let's see. So that's easy enough. We've done that plenty of times. The derivative of u cubed is going to be 3u squared. All right. So I'm not really interested though in u, right? Because we made this substitution over here for u. We called this part of it u. So let's go ahead and sub it back. 3, instead of u, I'm going to write 3x plus 1 squared. And you can see if you look at this, it makes sense when you look at here, right? Because all we did is we left g of x, which is 3x plus 1, alone. You just leave it there and you treat it almost as like a single variable. No matter what it is, you just say, okay, this is just one variable. And like in this case, we called it u. Right? And so we just took the derivative of this as if this was just a single, like an x or a u. So then we brought the 3 out front, made it squared, and then everything else on the inside stays the same. So now that would be step 1. We took the derivative of the outside function. Now the step 2 part is we multiply it by the derivative of the inside function. So the derivative of the inside function, we have derivative of 3x plus 1. Well, that just equals 3. So now we have step 1 and step 2, and we combine them, we multiply them together. So I'm going to have 3 times 3x plus 1 squared is that times this. So let's simplify it a little. 3 times 3, that equals 9. 3x plus 1 squared, and voila. There you have it. Okay, near the bottom of the page there. Okay, so let's take a look at another example then. Now that we can do trig functions, let's look at one with a trig function. How about, let's say we want to take the derivative of cosine x squared minus 1. Okay, up here we kind of did the long way about it, but let's abbreviate it a little bit. So I know the derivative of cosine equals negative sine. So since the derivative of cosine is negative sine, you're going to have negative sine, and then the inside stays the same. So you always leave this inside the same on the first part. Then you're going to multiply it by the derivative of that stuff on the inside, which is x squared minus 1. Well, the derivative of x squared minus 1, that just equals 2x. And the derivative of minus 1 is 0, so that just stays there. Now, simplifying this a little bit, I'm going to bring the 2x out front, so I have negative 2x sine x squared minus 1. And there we go. So that's it. Again, we took the derivative of the outside function, which is that, and we multiplied it by the derivative of the inside function. So let's take a look at just one more example. We're running out of space here, so let me flip this and get us back to the top of the page. There we go. All right, so sometimes with the chain rule, you'll have to use the chain rule with multiple steps or in multiple steps, and that's fine. I'm not sure if that's why it was called the chain rule initially, but it sort of makes sense. You know, if there's like links to a chain, you can link them all together. So let's take a look. This will be the last example here. So let's say you want to take the derivative of, let's say, sine squared of 2t squared. Whoops, that's a little bit high. There we go. All right, so anytime you see this squared value here, that really just translates to this. We're going to have sine of 2t squared squared. And the reason that it's written like this is, let's say if you wrote it out, it really saves you a lot of space, really. But if you had this out here, you know, then it would mean something totally different. It would mean you're going to square this value and then do one single sign, as opposed to this. If you see it right next to the sign, that means you're taking this, whatever the sign of this is, and then multiplying it, or I guess squaring it, multiplying it to itself. So this really means that. Okay, so now let's go ahead and start using the chain rule on it. So, all right. Well, first off, I know that the derivative, really first off, the derivative of something squared. All right, so let's call it, let's say if this was u, right here, right, u squared, the derivative of that is just going to be 2 times u. So that's sine of 2t squared. And then to the power of 1. All right, so that just stays the same. Now we're going to multiply this by the derivative of this u, which is sine of 2t squared. Now, looking at this, we say, well, we can't really do this in a single step because this, well, this is a composite function. This is also a composite function. But fear not, we have the chain rule, so we can just do the chain rule one more time. So we'll do it for another step, and then we should be able to get to something where we can just combine it all and make a single equation. So the first part stays the same, 2 sine of 2t squared. All right, and now this part. Well, the derivative of sine is negative cosine. So multiply negative cosine 2t squared. Again, the inside part, this u part, stays the same. And then I multiply it by the derivative of u. Well, all right, derivative of 2t squared, this will come out here. So I've got 4t to the first power, or just 4t. Okay, so let's see, looking at this, let's combine this to make it a little more simple. Here I've got a negative and a 4t. Let's multiply everything together. So I've got 2 times 4t, that's 8t, times this negative 1. So that's going to be negative 8t sine of 2t squared times cosine 2t squared. And I think that's as far as we're going to go. And there you have it. So you see, it's just the chain rule can be applied usually, at least with this intro chapter, it'll be mostly once, but sometimes you'll have to do it twice or 3 times, or really you could do it as many times as is necessary till you can get down to something that you can simplify.